Hello, I'm Bondi, and I would like to welcome you to this presentation. It's a pleasure to be here, and I would like to thank HorseTech for the opportunity to share my work with you. In this presentation, I would like to discuss the future of saddle design. We will unpick some aspects of the horse-saddle-rider interaction and consider some known knowns and some known unknowns. So, saddle design. Are we still in the dark ages? In 2006, I founded Solution Saddles, an innovation company which researches, designs, and manufactures the smart range of fully flexible sports saddles. My unique designs, which have been awarded 5 patents, have established the company as a market leader in saddles that promote equine welfare and performance. For its outstanding achievement, the company has won the Queen's Award for Enterprise in Innovation. It's the first time that a saddle design has won this coveted award. The award is the most prestigious for UK businesses, and this is a tremendous achievement. The role of the horse has changed from a source of food, work, and transport to one as a partner in sport and recreation. He has changed from a cash earner into a cash drainer. This changing role, inextricably linked to the needs of man, has dictated the way that the horse has been managed and trained to effectively exploit the horse's usefulness. The equipment we use in our use of the horse has also evolved. The 3 elements of the horse, saddle, and rider interaction form a complex coupled system. Each individual element influences the others, but also moves independently through its own individual freedoms of movement. Riding horses exposes them to increased risk of injury. It is therefore important, if public opinion is to continue to allow horses to be used for our pleasure at all, that we strive to develop our understanding of what may compromise the horse's welfare. The effects of being ridden are undoubtedly of great importance to the way in which the horse moves, behaves, and performs, but remain poorly understood. Common causes of poor performance in horses include factors related to the horse, the rider, or the saddle. And it's rare to find someone who has sufficient expertise in all 3 areas to be able to accurately diagnose the primary problem. The saddle is an important coupling. It translates movement from the horse to the rider and vice versa. Poor saddle fit to either the horse or the rider will disturb that crucial communication. The function of the saddle is to provide the interface between the horse and the rider. It should provide stability for the rider and reduce the peak forces exerted onto the horse's back by the rider. But does it? To be balanced and coordinated, the rider requires a narrow waist in the saddle seat. This narrow profile is mirrored in the narrow waist in the base panels. The horse, however, requires a wide gullet to avoid pressure on the spine and the sensitive support structures of the back. He needs room to bend and flex the thorax. The result is a lack of support and protection in a narrow panel, which does not spread load evenly and often leaves the bars of the rigid tree exposed with the risk of injury to the horse's back. To understand how saddle design has evolved, we need to look at military evolution. The earliest warrior horsemen from around 3000 BC simply vaulted onto the bare back of the horse. Blankets or animal skins provided better rider grip. Then surcingles followed to hold the blanket in place. Toe loops were then added to the surcingle to aid mounting. The first dependable representation of a rider with paired stirrups was found in China, dating from about AD 322. Stirrups added rider stability, but were the worst possible news for the horse. It changed everything. No longer just the rider's seat and legs gripping to stay on. Now there were peak pressure points and enormous force patterns caused by torque. Improved stability meant that the rider could stand up and use his hips, knees, and ankles as shock absorbers, which added greatly to the accuracy of weapon use. This, in turn, meant that the stirrups had to be held securely in place, so the earliest form of rigid framework or saddle tree was developed. This was essentially just two pieces of wood either side of the horse's spine, held together by arches at the front and the rear. Thus, we can understand how trees were originally made for the purpose of holding the saddle securely in place. By 700 AD, armored knights with shot weapons needed even greater security in the saddle. Holding a couch lance, dressed in heavy armor, and moving at speed towards an opponent saw the introduction of a cantle to prevent the knight being pitched backwards off his horse. By the 17th century, the cavalry saddle was equipped with armor plating designed to protect the rider and hold them in place. However, there's an interesting reference to these reinforcements being responsible for major injury to the rider in the event of the horse falling. All weapon usage put a tremendous strain on the saddle. The vigorous movements of the rider and the horse revealed any weakness in saddle construction. The strain and movement exerted by the saddle to the horse's back caused pressure galls and open wounds. It's said that during the Napoleonic Wars, the French army could be smelt by the stink from their horses' festering backs. Thus, we can see that the development of the form of the saddle was derived from its necessary function, which was first and foremost rider stability and not the comfort of the horse. So at this point, we can bust two popular myths. One, the saddle did not evolve to provide comfort for the horse. On the contrary, it is a damage limitation design. And two, good saddle design reduces peak pressures, but it can never evenly distribute weight or force between dynamic interaction of horse and rider. So, has saddle design progressed? Well, yes, but mainly no. If we compare saddle design through the ages, we can observe that they all have the same features. Rigid halves sitting either side of the horse's spine, held together by arches at the front and the rear. The design hasn't altered because the function has not altered. Rigid parts of the tree in a conventional saddle create focal pressure points. A conventional saddle tree must be well padded to avoid injury to the horse's back from the tree. The base panels should provide even support. There are many manufacturing defects in today's saddles, including, as seen here, asymmetric base panels. If the saddle tree is too wide, as seen here, the tree points exert focal pressure. The stirrup bar may be recessed to provide greater comfort for the rider, but this can cause injury to the horse instead. Albert Einstein said, "Nothing happens until something moves." But in the case of horse, saddle, and rider interaction, when things start moving, unexpected things can happen. The horse's back movement has 6 degrees of freedom, and this is translated as accelerations through the saddle to the rider. This movement is easy to understand if you visualize how a ship moves through the water, or in this illustration, how an airplane moves through the air. Let's consider how the horse's back moves the rigid saddle tree through the 6 degrees of freedom. The movement of the horse's scapulae, back, ribs, and pelvis all create movement of the saddle through its 6 degrees of freedom. The 6 degrees of freedom comprise 3 linear movements and 3 rotational movements. The linear movements are vertical, up and down. horizontal, forwards and backwards, and lateral, left and right. The rotational movements center around one point. Each gait has different quantities of rotation. In trot, the saddle rotation is mainly roll. In canter, the rotation is mainly pitch around the same center point. In walk, the rotation is mainly yaw, that is a diagonal rotation. The weight of the rider adds force to the rotations, creating torque around the center point. Let's look at the rotational movement of the saddle on the static horse's back. We can observe the 6 degrees of freedom of the saddle movement on the back. In trot, the rotation is mainly roll. In canter, the rotation is mainly pitch. And in walk, the rotation is mostly yaw. But what happens when the horse moves? The horse's back movement is translated through the saddle to the rider. The manner in which the horse carries the rider will affect the posture and balance of the rider. As the horse moves, the scapulae rotate backwards against the tree points. When turning, the inside scapula rotates further backwards. So now let's observe the movement of the tree on the horse's back during turning. The movement of the horse's scapulae, ribs, back, and pelvis all contribute to the movement of the saddle. Transient peak pressures are created by this movement, but in a well-fitting saddle, this movement is regular and predictable. When base panels are correctly fitted, they will attenuate some of this movement, but when the weight of the rider is added, the forces increase. In an ill-fitting saddle, its movement on the horse's back becomes more irregular. This saddle is too narrow and too curved for this flat-backed horse, causing an irregular and unpredictable movement pattern that will create higher peak forces. Motion pattern stability is important because it allows coordination and synchronization between horse and rider. This in turn leads to that holy grail of riding, harmonization. The saddle should remain central on the horse's back in all gaits and during turns and changes of direction. Slight movement from side to side is normal, but the saddle should not swing from side to side, slide forwards or backwards, bounce, or lift off the horse's back at the rear. A rigid treed saddle twists across the back as the horse turns due to the rotation of the scapula. The saddle in turn pushes the rider out. This rolling saddle provides an unstable platform for the rider. Riders of round-backed horses are usually more aware of a poor fit because the saddle is more likely to roll. To help hold the saddle in place, it's quite common to see the tree-point girth straps used in an attempt to provide stability. If the saddle moves excessively, riders often resort to over-tightening the girth. But over-tightening the girth can cause myofascial tears and adhesions in the girth region, as we can see here. If a saddle is too narrow, the rear may lift off the horse's back because it cannot accommodate the movement of the horse's shoulders and back. We can see in this jumping saddle how much the cantle has lifted away from the back. If the saddle is too narrow, the scapulae will lift the tree points up as they rotate under it, causing the saddle to ride forwards up the neck. When the tree points interfere with the movement of the shoulder, the saddle may be pushed backwards. Excessive saddle movement may cause friction rubs. Damage to the hair follicles can be caused by pressure, heat, and/or friction, and this may result in patches of hair loss or white hair. Muscle atrophy depressions caused by excessive pressure are frequently found behind the scapulae under the tree point area. Asymmetric patches of hair wear under the back of the saddle may be caused by rider or saddle asymmetry, but are more likely to be caused by saddle slip associated with hind limb lameness. Dry patches under the tree points and stirrup bars surrounded by areas of normal sweating may indicate excessive pressure. A normal pattern of sweat and dry areas can be seen here. Movement of the fore and hind limbs create more movement at the front and rear of the panels, but the central area should remain relatively stable. So let's look at some innovations in saddle design to try and resolve these problems. Traditional saddle makers have tried to overcome the problem of how to make a rigid frame that is designed to help the rider fit comfortably on a horse that needs to be able to move freely. This is an early example of creative thinking, which features rotating base panels. And these offer flexibility in fitting to different back profiles. Saddle designers have tried in different ways to make trees more flexible. This design, which has since disappeared from the market, featured an upper tree which could slide along a base tree with a shock absorber. It's important to understand what the framework inside the saddle is comprised of, and what it's specifically designed to do, and the effect that this will have on the horse. This design features shock-absorbing discs, which attach the flexible panels to the saddle tree, but this is still a rigid tree. This saddle has a hinged headplate design. This design is a rigid plastic tree that has a removable steel reinforced headplate, allowing alterations to the width of the front of the tree. Air-filled bags have become popular because they're easily adjustable. And this is the ultimate airbag design. It's a fully inflatable saddle. This British-designed inflatable saddle saves many pregnant women's lives in the remote mountains of Afghanistan by getting them to hospitals when there are no other methods of transport available. This is a cantilever design. And this is another cantilever design which failed. But how are new saddle designs tested? How do we know how they work, or indeed if they work at all? So we can see from all of these design innovations that saddle designers have increasingly tried in different ways to make trees more flexible. Whilst treeless saddle makers started with floppy pads like this bareback pad, and added some rigid parts to give more structure. So-called treeless saddles are actually part-treed and include a rigid structure, and this is usually a pommel arch, which raises the saddle off the wither. This type of design usually leaves the girthing assembly and stirrup hanger unsupported. This will not avoid peak pressure points, but will actually increase them. This type of design cannot support correct rider posture and efficient rider biomechanics. It is not a rider's tool to enable them to synchronize more easily with the horse, and I use the term leisure pad, not saddle, to define them. It's therefore crucial to understand how an individual design will function on the horse's back to ensure the long-term comfort of the horse. Although starting at opposite ends of the spectrum, the two types of saddle manufacturer, that is the traditional treed and the alternative treeless, are moving towards each other in trying to reach the same place. And this is the sweet spot in the middle of the design spectrum. And this is where the smart technology is located. The technologically advanced smart saddle has moved forwards in manufacturing techniques by incorporating substance to help spread the load over a wider weight-bearing area, whilst remaining 100% flexible. This unique concept incorporates the HorseTech panel system, which comprises layers of high-tech materials selected for their physical properties. The result is a high-functioning panel which protects the horse's back from high peak pressures by damping vibration, absorbing concussion, and reducing shear force. Bicycle saddles, although different in shape, have some functional design requirements in common with a horse saddle. E.g., both are required to provide leverage for stability. The front of the saddle is a balance point for the thigh. The thigh is then able to create directional influence. I love this action shot. Andrew Nicholson demonstrates perfect synchronization with Nerio. The horse is completing the airborne phase of the jump completely straight, but Andrew is already signaling with thigh leverage from his right leg that he wants to turn left. The weight pushing down into his left stirrup is adding to the force of the lever. But this image also demonstrates how the rigidity of the saddle tree increases the mechanical steering lever of the rider and therefore increases torque. This concept is important to understand more fully because of the currently unknown effects that levers and torque have on the magnitude of the forces exerted on the horse's back. Torque is a rotational force. Just as a linear force is a push or a pull, a torque can be thought of as a twist to an object. The magnitude of torque depends on three quantities: the force applied, the lever length, and the angle between the force and lever arm. Jumping entails very active levers with undoubted torque exerted on the horse's back through the saddle, but this has never been measured. The combination of the rider's weight, their height, and posture will affect their use of active levers. A tall rider has longer levers, which will increase torque. The heavier rider's weight will also increase the force of the lever, which will in turn increase torque. The rider is connected to the horse's back via the saddle and uses leverage as part of the coping strategy to help them maintain stable phase synchronization with the horse's movement. This video clip is a clear example of asynchrony of the three elements, where the rigid saddle creates an unstable platform for the rider. The rider's pelvis remains in alignment with the rigid saddle as it moves, not the horse's back, with clear loss of synchrony. The rider's compensatory movements and use of levers help to maintain their balance. The pitching rotation of the saddle in canter and the asymmetry of the gait combine to create obvious torque patterns, affecting both the horse and the rider. This rider had lower back pain, and it's easy to see here how her posture is affected in a negative way by torque. Of course, it's not just the rider who's affected in a negative way by torque. The images show a round back on the left and a narrow or razor back on the right. In either type of conformation, there can be a torque point on the horse's back caused by the lateral branches of the tree. usually where the tree is at its narrowest, the waist. The soft tissue can become pinched between the tree and the top of the spinous processes. It's common to see muscle inflammation, as in the image on the left, or ligament inflammation, as in the image on the right. Because it's extremely difficult to check the saddle fit in this area, this problem often goes unrecognized. A smart, flexible saddle design functions like a Nike trainer on your foot. It is more stable because it flexes with the movement and therefore eliminates torque for both the horse and the rider. When a ridden horse experiences discomfort, he may express this in many different ways. Abnormal behaviors are extremely common during tacking up and may be an indication of anticipation of discomfort when being ridden. Signs of resentment may include fidgeting, tail swishing, kicking, putting the ears back, head tossing, opening the mouth, or biting. These are not normal behaviors, but owners often become accustomed to them. In the images on the left, the eyelids are closed and the ears are back behind a vertical position during noseband tightening. In the image on the right, the horse is tossing its head during saddle placement and the ears are back. Although the trained horse should stand still to be mounted, he may move in anticipation of pain or discomfort when being mounted or ridden. Some horses may even resist going towards the mounting block or attempting to move away before the rider has mounted. Signs of saddle-related problems in the ridden horse are often the same as may be exhibited by the horse for any other pain-related issue, such as sharp teeth or lameness, making it difficult to decide where the primary cause may be. A simple diagnostic method is to change the saddle for one that fits more comfortably. In this way, the saddle can be ruled in or out as the primary cause of poor performance problems. For this reason, the smart saddles are used by veterinary clinicians to aid diagnosis in poor performance cases. The fully flexible smart saddle design moves with the horse's back and shoulder movement, helping to eliminate friction, torque, and peak pressure points. Measurement of the forces exerted by the smart saddle onto the horse's back whilst being ridden show an even, regular pattern. A horse that's working comfortably should move forward freely without resistance. Although often considered to be training or temperament issues, resistance, reluctance, tension, or rushing are usually signs that the horse has pain or discomfort. A horse that's able to work pain-free should find the work easy, and the rider should find the horse easy to ride. This horse holds his top line stiffly and is reluctant to go forwards. This is a typical way of going in a horse that is restricted by a rigid tree. When changed to a smart saddle, he relaxed his neck and stretched forwards, moving with longer, swinging steps. In eventing, the introduction of deformable fences has helped to prevent some rotational horse falls, but they cannot eradicate them completely. Are rigid steel frame saddles implicated in the severity of the rider injury or even the death of the rider in the event of the horse falling on the rider? In a rotational fall, the rider is trapped under the horse. We don't know which bit of the horse impacted on which bit of the rider because this data is not yet recorded by event officials in accident report forms. Clearly, there's a need for more detailed information concerning the causative factors involved in the severity of rider injury or death in the event of the horse falling on the rider. Deformable saddles could potentially reduce the risk of injury to the rider in the event of the horse falling on them. This horse is wearing a deformable saddle. It's a fully flexible smart saddle, and neither the rider nor the horse were injured in this fall. Interestingly, the saddle was also completely undamaged. The technical materials simply absorbed the impact. We can understand now how the welfare, performance, and safety of the rider are enhanced by the smart saddle design concept. An added bonus is that the smart range of saddles look both conventional and modern. Beautifully handcrafted by skilled saddle makers in Derbyshire, even the most bling-inspired riders can now choose their own unique, customized style. We all have an effect on the horse every time we ride. It's up to all of us to minimize any negative impact and maximize the positive effects. Thank you for your attention.